Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this green shape, and in the second question, we'll find out the length of this line segment PQ is equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing, we have a circle inside this big semicircle. In addition, we know that this is line segment AQ, that is equals to 4 units in its length. This is line segment TB, that is equals to 1 unit in its length. This is angle PQA, that is a right angle. This is angle STB, that is also a right angle. Again, our task is to find out the area of this gray shape. So first of all, we will define the radius of the big semicircle Sx and the radius of this small circle Sy. In addition, we will define the center of this small circle. This point is point O, and we will define the center of this big semicircle. This point is point C. Likewise, we will define the point of tendency of tangent AB with this circle. This point is point N. We define the point of tendency of tangent ST with this small circle. This point is point L. We will define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we will define the touching point of this small circle with this big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of this small circle. Point N is the point on the small circle itself. Therefore, ON is the radius of this small circle. That is equals to y according to our definition. The radius ON, that is equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is a right angle according to what is given in the question. AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB, it's point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB, it's point Q. We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Again, rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have? So the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if you focus on the upper side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point D? We have this angle that is equal to 90 degrees in its size according to what is given to the question, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and M together by straight line. OL is of course the radius of this small circle that is equals to y. The radius OL that is equals to y, the radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral ONTL, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle not a square. So in order to quadrilateral OLTN, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL equals to y, therefore the opposite side TN must be also equal to 1 units in its length. Likewise, we join points O and H together by straight line. OH is of course the radius of this small circle that equals to y. The radius OH that equals to y, the radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in quadrilateral HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral HO and Q, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle not a square. So we unite quadrilateral HO and Q as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HOQN, side HO must be equal to the opposite side QN. But HO equals to y, therefore the opposite side QN must be also equal to y units in its length. This is line segment QT that is part of the diameter AB. The diameter AB is a diameter that is absolutely straight line. So QT is a part of a straight line. A part of a straight line must be also a straight line. So QT is a straight line, and QT in total equals to y plus y, that is 2y. QT equals the straight line QT equals to 2y units in its length. the diameter AB is twice as long as the radius of the semicircle. The radius of the semicircle is x, therefore the diameter must be equal to 2x. So write it down. From one side, the diameter AB equals to 2x units in its length. It is twice as long as the radius of the semicircle. But from the other side, the diameter AB equals to AQ plus QT plus TB. Again, the diameter AB in total equals to AQ plus QT plus TB. So I'll write it down. If you found out that AB, the diameter AB equals to AQ plus QT plus TB. AB equals to 2x and 2x equals to AQ. AQ is 4 according to what is given us in the question, plus QT. We just right now found out that QT equals to 2y units in its length, plus TB. TB equals to 1 unit in its length. So in total, we actually found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y and 4 plus 1 is 5. So 2x in total equals to 2y plus 5. Here we subtract 2y from this equation and we get that 2x minus 2y equals to 5. Here we'll take out 2 as a common factor from those two expressions. Inside the brackets we will have x minus y. So in total we found out that 2 times x minus y equals to 5. Here we will divide this equation by 2 and finally we get that x minus y equals to 5 over 2. 5 over 2 is 2.5. So if we found out in total that x minus y equals to 2.5. What is the length of this line segment? Line segment CN. From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. So I write it down. Actually found out that CN equals to CB minus NT minus TB. So, again, Cn equals to Cb minus Nt minus Tb. So, Cn equals to Cb. Cb is the radius of this semicircle. This equals to x minus Nt. Nt equals to y minus Tb. Tb equals to 1 unit in its length according to what is given us the question. So, in total, we actually found out that Cn equals to x minus y minus 1. So Cn equals to x minus y. X minus y is 2.5. Therefore, we will substitute x minus y in this equation by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we actually found out that Cn equals to 1.5 units in its length. This is 9 segments in the end, that is equals to 1.5 units in its length. In the next step, we will repeat on rule 9 and we will implement rule 9 in our drawing. We have already talked about rule 9 in the previous lessons. according to rule 9, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. In the drawing, we have two circles. The center of this big circle is here at point O. The center of this small circle is here at point M. The straight line that connects the circles together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through the touching point, that is point P. Again, the straight line OM that connects their centers together must pass through point P, that is their touching point. Or in other words, OMP is one straight line. Again, according to rule 9, OMP is one straight line. So we can actually implement rule 9 in our drawing. Why? Because in our drawing, we have an internal notch between the small circle and the big semicircle. That is to say, they touch each other internally at this point K. And whenever you have an internal notch between two circles or a semicircle, you can implement rule 9. So we will implement rule 9 in our drawing. The center of this big semicircle is here at point C. The center of this small circle is here at point O. And the straight line that connects their centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through their touching point, that is point K. Again, according to rule 9, the straight line CO that connects their centers together must pass through their touching point, that is point K. Or COK is one straight line. Again, COK is one straight line according to rule 9. So we will join point C and O together by straight line, and according to rule 9, the straight line CO must pass through their touching point, that is point K. From the drawing, it is very easy to see that CO, that is the straight line that connects their centers together, indeed passes through point K, that is their touching point. Or COK is one straight line. Exactly according to rule 9. Again, from the drawing, it is very easy to see that the straight line CO passes through point K, that is their touching point. Or COK is one straight line. So if COK is one straight line, it means that CO must be equal to CK minus OK. Again, CO equals to CK minus OK. So I write it down. If you found out that CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that is equals to X minus OK. OK is the radius of the small circle, that is equals to Y. So in total, we actually found out that CO equals to X minus Y. CO equals to X minus Y. But we have already found out that X minus Y equals to 2.5. So CO equals to X minus Y and X minus Y equals to 2.5. Therefore, CO equals to 2.5 units in its length. In the next step, I'll copy the right triangle O and C in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle O and C. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right angle CON that are going to undergo drawing. This right angle CON, OC squared, that is the square of the hypotenuse, equals to ON squared plus MC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared, plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, that is 2.25. So in total we found out that 6.25 equals to y squared plus 2.25. Here we will subtract 2.25 from this equation, and we get that 6.25 plus 2.25 is 4. So 4 equals to y squared. Here we take a root out of this equation, and finally we get that y equals to the square root of 4, that is 2. So if you found out that the radius of the small circle y is equal to 2 units in its length. We already found out that x minus y equals to 2.5. We already found out that x minus y equals to 2.5. Y is 2, so we substitute y by 2, and we get that x minus y is x minus 2 equals to 2.5. Here we add 2 to this equation, and we get that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So if we found out that the radius of the big semicircle, x equals to either 9 over 2 units in its length, or in terms of numbers, it is equal to 4.5 units in its length. Our task is to find out the area of this grand semicircle. Again, our test is to find out the area of this grand shape. So what is the area of the grand shape? The area of the grand shape, from the drawing it is very easy to see that the area of the grand shape equals to the area of the big semicircle minus the area of the small circle. Again, the area of the grand shape in total equals to the area of the big semicircle minus the area of the small circle. So write it down. The area of the grand shape in total equals to the area of the big semicircle minus the area of the small circle. What is the area of the big semicircle? We know that the radius of the big semicircle is x. Therefore, the area of the big semicircle must be equal to pi x squared over 2 minus the area of the small circle. The radius of the small circle equals to y, therefore the area of the small circle must be equal to pi y squared. So today we found out that the area of the grand shape equals to pi x squared over 2, that is the area of the semicircle, minus pi y squared, that is the area of the small circle. X is 9 over 2, so we solve x by 9 over 2 in this equation, and we get that we have here pi over 2. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression equals to 9 over 2 times pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4, so pi y squared is actually 4 pi. Here we open the brackets of this expression and get that we have here pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So today we found out that the area of the semicircle equals to 81 pi over 2 times 4 minus 4 pi. 2 times 4 is 8, so in total this expression is equals to 81 pi over 8. 81 pi over 8 is the area of the big semicircle minus 4 pi. 4 pi is the radius of the small circle. So here we multiply 4 pi by 8 and then we divide it by 8 in order to overcome factor with this expression, and we get that minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 32 pi is 49 pi. 49 pi over 8. So if you found out that the area of the green shape, that is the area that we are looking for this question, it is equal to either 49 pi over 8 square units in its size, or in terms of numbers, 49 pi over 8 is 19.24 square units in its size. And again, we actually found out that the area that we are looking for in this question that is the area of this ring shape is equal to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing you have a semicircle. It is given us the question that this is point O, that is the center of this semicircle. This is line segment OS, that is equals to 2 units in its length. This is line segment SV, that is equals to 1 unit in its length. This is angle PQB, that is a right angle. This is angle PTS, that is also a right angle. Again, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. It is given us the question that line segment PT equals to line segment TS. So if we define the length of line segment PT as A, then the length of line segment TS must be also equal to A, because they are equal to each other. In the next step, we will complete this semicircle to a circle. and we will extend 970s by a straight line until it touches the circle. We will define the touching point of the extended 970s with this circle. This point is point M. In the next step, we join points P and M together by a straight line. By doing all those constructions, we created triangle PTM. This is triangle PTM. This is equals to 90 degrees in its size according to what is given as the question, and triangle PTM subtend on chord QM. Again, triangle PTM subtend on chord PM. So here we can implement rule 5. I'll click quickly on rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees in its size must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral MAN. This is equals to 90 degrees in its size. And therefore peripheral MAN, according to this rule 5, must subtend on the diameter of the circle. And indeed peripheral MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equals to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing we have triangle PTM. Triangle PTM equals to 90 degrees in size according to what is given as the question, and therefore according to rule 5, triangle PTM must subtend on the diameter of the circle. Again, because of the fact that triangle PTM is equal to 90 degrees in its size, according to rule 5, it must subtend on the diameter of the circle. Triangle PTM subtend on chord PM, and therefore according to rule 5, chord PM must be the diameter of the circle. So on the line we found out that chord PM, this is chord PM, that is the diameter of this circle according to rule 5. It is given us the question that point O is the center of the circle, point B is the point on the circle itself, therefore OB is the radius of this circle. OB in total equals to OS, that is 2, plus SB, that is 1. So in total OB equals to 2 plus 1, that is 4. Therefore the radius of this circle is equal to 3 units in its length. The radius OP equals to 3 units in its length, and the radius OM is also equals to 3 units in its length. In the next step, we will do a construction. That is to say, from point S, we will do perpendicular on the diameter PM. Again, from point S, we will do perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles, so you know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right lower triangle SON, this angle equals to alpha, this angle equals to 90 degrees, and therefore this promising angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. We prove that those two right angles are similar to each other according to angle similarity rule. So why those two right angles are similar to each other? Why the upper right triangle PQO is similar to the lower right triangle ONS? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the angles of this upper right triangle PQO are correspondingly equal to all the angles of this right lower triangle OSN, and therefore those two right triangles are similar to each other according to angle similarity rule. So as you know, if you found out that the upper, if you found out all the figures of the upper right triangle PQO are correspondingly equal to all the figures of this right lower triangle OSN, therefore those two right triangles are similar to each other. So if you found out the upper right triangle PQO is similar, this is the sum of similar to the right lower triangle OSN, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle OSN over side PO of the upper right triangle PQO. Which is again from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle OSN over side PO of the right upper triangle of the right upper triangle PQO. SN is the missing side, so we leave it as it is. Over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. We have to find out the value of x. And it is equal to OS. OS equals to 2 units in its length according to what is given in the question. Over PO. We have already found out that PO is the radius of this circle, that is equal to 3 units in its length. So the circle equals to 3. So in total, we actually found out that Sn over x equals to 2/3. Again, Sn over x equals to 2/3. Here we will multiply this equation by x and finally get that the missing side Sn equals to 2/3 x. Again, the missing side Sn equals to 2/3 x. This is the missing side Sn is equal to 2/3 x units in its length. So I want to know Sn equals to 2/3 x. In the next step, we will define this angle as beta, and we will focus on the right small green triangle SNM. This is the right small green triangle SNM. This right small green triangle SNM, this angle equals to beta. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle equals to beta, and therefore angle beta is the common angle that belongs to both triangles. Angle beta belongs to the green triangle SNM, and angle beta also belongs to the big right triangle PTM. So this in the right big triangle PTM, this is angle beta, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this small green right triangle NSM. So why those two right triangles are similar to each other? First of all, this is angle beta, that is a common angle that belongs to both triangles. So I can write down that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So if you prove that all the three angles of this big right triangle PTM are correspondingly equal to all the three angles of this small green triangle NSM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PTM is similar, this is the sign of similar, to the small right green triangle NSM, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side Sn of the right small green triangle NSM over side PT of the big right triangle PTM is equal to side SM of the green small right triangle NSM over side PM of the big right triangle PTM. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side Sn of the green small right triangle NSM over side PT of the big right triangle PTM is equal to side SM of the green small right triangle NSM over side PM of the big right triangle PTM. NS equals Sn equals to 2/3 x over PT. PT, this is sine PT, this is equals to A units in its length according to our definition. And it is equals to SM. SM is the missing side, so we leave it as it is. Over PM. PM is the diameter of this circle. The radius is 3, therefore the diameter is 6. So PM equals to 6 units in its length. The diameter of PM equals to 6 units in its length. So here we of course multiply this equation, and we'll get that 2/3 x times 6 equals to ASM. This will be equation 1. According to equation 1, we found out that 2/3 x times 6 equals to ASM. We have here 6 over 3 is 2, and 2 times 2x is 4x. So in total, in this equation 1, we have 4x. So 4x equals to ASM. According to equation 1, we found out that 4x equals to ASM. In the next step, I repeat on rule 15, and we'll implement rule 15 in our drawing. We have already talked about rule 15 in the previous lectures. So we'll do it quickly. According to rule 15, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. In the drawing, we have a circle. This is chord AB. It intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this drawing, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Why? Because in our drawing, we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15 in our drawing. So to now we should find out that in our original drawing, chord TM intersects with chord AB at point S. The intersection point of chord AB with chord TM occurs at point S. So we can implement here rule 15. According to rule 15, the following equation will be true. That TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. So I write it down. If you found out that according to rule 15, TS times SM equals to AS times SB. Then again, according to rule 15, we found out actually that TS times SM equals to AS times SB. This is equation 2. TS equals to A units in itself according to our definition, times SM. SM is the missing size of the unit cities. So this is the equation 2. We have A times SM equals to AS. AS in total equals to AO plus OS. AO is the radius of this circle that is 3 plus OS that is 2. So in total AS equals to 3 plus 2, that is 5. AS is 5 times SB. SB equals to 1 unit in itself, according to what is given as the question. So in total we found out that according to equation 2, A times SM equals to 5 times 1. 5 times 5 is 5. So in total we found out that according to equation 2, A times SM equals to 5. This is according to equation 2. Well, according to equation 1, we would find out that A times SM equals to 4x. According to equation 1, we would find out that A times SM equals to 4x. So we have two different equations for the expression ASM. Therefore, we will create the equation 3 that says that A times SM according to equation 1 must be equal to A times SM according to equation 2. Repeat again, equation 3 states that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times SM according to equation 1 equals to 4x, and it must be equal to A times SM according to equation 2. A times SM according to equation 2 equals to 5. So in total according to equation 3 we actually found out that 4x equals to 5. Here we will divide this equation 3 by 4, and finally we get that x equals to 5 quarters. 5 quarters is 1.25 units. So if you found out that the length of this line segment PQ is equal to x, it is equal to either 5 quarters units in itself, or in terms of numbers, the length of this line segment PQ that is equal to x is equal to 1.25 units in its length. And again, PQ that is equal to x is equal to either 5 quarters units in itself, or in terms of numbers, PQ that is equal to x is equal to 1.25 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the drawing we have a circle inside this big semicircle. This is line segment AQ that equals to 4 units in its length. This is line segment TB that equals to 1 unit in its length. This is angle PQA that is a right angle. This is angle STB that is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x, and the radius of this small circle as y. Likewise, we define the center of this small circle, this point as point O, and we define the center of this big semicircle, this point as point C. We define the point of tendency of tangent AB with this small circle, this point as point N. We define the point of tendency of tangent PQ with this small circle. This point is point H. We define the point of tendency of tangent ST with this small circle. This point N. This point is point N. We define the touching point of this small circle with this big semicircle. This point is point K. We know that AB is the diameter of the semicircle. The radius is x. Therefore, the diameter AB must be equal to 2x units in its length. In the next step, we join points O and N together by straight line. Point O is the center of this small circle. Point N is the point of the small circle itself. Therefore, ON is the radius of this circle. That is equals to y according to our definition. The radius ON that is equals to y. The radius ON is drawn to point N. That is the point of tendency of tangent AB with this small circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is right angle according to what is going to the question. AB is the diameter of this semicircle. So AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the next step, likewise, if you focus on the upper side of the side A, if you focus on the upper side of the side line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So, which angles we have at the upper side of AB at point T? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and L together by straight line. OL is of course the radius of this small circle, that is equals to y. The radius OL is equals to y. The radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th missing angle must be equal to 90 degrees in its size. So in quadrilateral OLTN, we have 4 right angles, and according to rule 5, any quadrilateral that says 4 right angles must be this rectangle in front of square. So in that quadrilateral OLTN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OLTN, side OL must be equal to the opposite side TN. But OL equals to y, therefore the opposite side TN must be also equal to y units in its length. In the next step, we join points O and H together by straight line. OH is of course the radius of this circle, that is equals to y. The radius OH, that is equals to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in quadrilateral edge O and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral edge O and Q, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be its rectangle plus a square. So we write for the other edge O and O, edge O and Q as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle edge O and Q side edge O must be equal to the opposite side QN. But edge O is right, therefore the opposite side QN must be also equal to Y unit in its length. QT is part of the diameter AB, and the diameter AB is a straight line, therefore QT must be also a straight line because part of a straight line must be also a straight line. Therefore QT is a straight line, therefore the straight line QT in total equals to QN, that is Y, plus NT, that is also Y. So in total QT equals to 2 Y units in its length. Again, the straight line QT equals to 2 Y units in its length. The diameter AB is twice as long as the radius, so therefore it is equal to 2x from one side, but from the other side, the diameter AB also equals to AQ plus QT plus TB. Again, the diameter AB in total equals to AQ plus QT plus TB. Okay, again, from one side, the diameter AB of the semicircle equals to 2x, but from the other side, the diameter AB also equals to AQ plus QT plus TB. AQ is 4, TB is 2y, again AQ is 4, QT is 2y, and TB is 1. So in total, 2x equals to y, 2x equals to 4 plus 2y plus 1. 4 plus 1 is 5, so in total, 2x equals to 2y plus 5. Here we subtract 2y from this equation, and we found out that 2x minus 2y equals to 5. Here we took 2 as a common factor from those two expressions, so inside the brackets we left with x minus y. So in total we found out that 2 times x minus y equals to 5. Here we divided this equation by 2 and found out that x minus y equals to 5 over 2. 5 over 2 is 2.5. So in total we found out that x minus y equals to 2.5. What is the length of this line segment CB, CN? CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. And again, in total, CN equals to CB minus NT minus TB. So CN equals to CB. CB is the radius of the semicircle, that is x, minus NT. NT is 1, TB is 1. So in total, we found out that Cn equals to Cb is x, minus NT is y, minus Tb, that is 1. So in total, Cn equals to x minus y minus 1. X minus y is 2.5, therefore we substitute x minus y by 2.5. So in total, we found out that Cn equals to 2.5 minus 1. 2.5 minus 1 is 1.5. So we found out that the length of this line segment Cn is equals to 1.5 units. In the next step, I presented to you Rule 9 and implemented Rule 9 in our drawing. According to Rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. Again, if two circles touch each other internally, then the straight line that connects the circles together passes through their touching point. In the drawing, you have two circles. The center of this big circle is 0.0. The center of this small circle is 0.10. The straight line that connects the circles together is of course the straight line OM. And according to this Rule 9, the straight line OM must pass through point P, that is the touching point. Again, the straight line OM must pass through the touching point, that is point P. For O and P is one straight line. Again, O and P is one straight line according to this Rule 9. So we can implement Rule 9 in our drawing. Well, because in our drawing, we have an internal notch between this small circle and this big semicircle. That is to say, they touch each other internally in this point K. Whenever you have an internal notch between two circles or semicircles, you can implement Rule 9. So we'll implement Rule 9 in our drawing. The center of this big semicircle is 0.3. The center of this small circle is 0.0. The straight line that connects the circles together is of course the straight line CO. And the straight line CO, according to Rule 9, must pass through the attaching point, that is point K. Again, the side angle CO must pass through point K, that is the attaching point. Or COK is one side line. Again, according to rule 9, COK is one side line. If COK is one side line, it means that CO equals to CK minus OK. And again, CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that is X, minus OK. OK is the radius of the small circle, that is Y. So in total, we found out that the length of line segment CO is equal to X minus Y. But X minus Y is 2.5. We only found out that X minus Y equals to 2.5. So CO equals to X minus Y, and X minus Y equals to 2.5. And therefore the length of line segment CO is 2.5. In the next step, I copied the right triangle CON in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle CON. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle OCN that are going from the original drawing. This right triangle OCN, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. Again, OC squared equals to ON squared plus CN squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared, plus CN squared. CN is 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total, we found out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation, and finally found out that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we took a root out of this equation and found out that y equals to the square root of 4, that is 2. So we found out that the radius of the small circle y equals to 2 units in its length. We already found out that x minus y equals to 2.5. Y is 2, so we substitute y by 2, and finally found out that x minus y is x minus 2, that is equals to 2.5. Here we added 2 to this equation, and finally found out that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So she found out that the radius of the big semicircle, x equals to either 9 over 2 units in itself, or in terms of numbers, the radius of the semicircle x equals to 4.5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape must be equal to the area of the big semicircle minus the area of the small circle. So again, the area of the green shape in total must be equal to the area of the big semicircle minus the area of the small circle. What is the area of the big semicircle? The radius of the big semicircle is x, therefore the area must be equal to pi x squared over 2. So the area of the semicircle equals to pi x squared over 2 minus the area of the small circle. The radius of the small circle is y, therefore the area of the small circle must be equal to pi y squared. The radius x of the semicircle equals to 9 over 2, therefore x squared equals to 9 over 2 squared. So in total this expression pi x squared over 2 is equal to pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, so y squared is 2 squared, it is 4. So in total this expression equals to 4 pi. We open the brackets here, and we found out that this expression equals to pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, over, that is 81, over 2 squared, that is 4. So in total we found out that the area of the big semicircle equals to 81 pi over 2 times 4, and the area of the small circle is 4 pi, so it is minus 4 pi. 2 times 4 is 8, so in total this expression equals to 81 pi over 8 minus 4 pi. So here we multiplied minus 4 pi by 8, and then we divided by 8 in order to overcome a factor with this expression. And finally found out actually that minus 4 pi times 8 is minus 32 pi, so in total in the numerator we have 81 pi minus 32 pi, that is 49 pi over 8. So if you found out that the area of the green shape equals to either 49 pi over 8, coordinates in size, so in terms of numbers, 49 pi over 8 is 19.24 square units in its size. Okay, again, if you found out that the area of this green shape, that is the area that we are looking for this question, is equal to either 49 pi over 8 square units in its size, so in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finished with the first question. In the next step, I presented to you the second question and answer to the second question of this lecture. In the second question, our test is to find out the length of this line segment PQ is equal to x. So we have to find out the value of x. So in the drawing, we have a semicircle. Point O is the center of this semicircle. This is line segment OS, that is equal to 2 units in its length. This is line segment SB, that is equal to 1 unit in its length. This is angle PQB, that is a right angle. This is angle PTS, that is also a right angle. And we know that PT equals to TS. So if we define the length of PTSA, then the length of TS must be also equal to A because they are equal to each other. Again, our test is to find out the length of this line segment PQ that equals to x. We have to find out the value of x. So first of all, we completed this semicircle to a circle, and we extended line segment TS by side line until it touches the circle. We define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we join points P and M together by side line. By doing all those constructions, we can do the peripheral angle PTM. Peripheral angle PTM equals to 90 degrees in its size according to what is given as the equation, and peripheral angle PTM subtend on chord PM. Again, peripheral angle PTM subtend on chord PM. So we can implement a rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size, like this peripheral angle PTM, must subtend on the diameter of the circle. Peripheral angle PTM equals to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Peripheral angle PTM subtend on PM, and therefore PM must be the diameter of the circle according to rule 5. The diameter of the circle is PM according to rule 5. Point O is the center of this circle according to what is given as the equation. Point B is the point of the circle itself, therefore OB is the radius of this circle. OB in total equals to OS, that is 2, plus SB, that is 1. So OB in total equals to 2 plus 1, that is 3. So if you found out that the radius of this circle is equal to 3 units in its length. So the radius PO, the radius OP of this circle equals to 3, and the radius OM of this circle must be also equal to 3 units in its length. In the next step, we did the construction, that is to say from point S, we do perpendicular on the diameter PM. Again, from point S, we do perpendicular on the diameter PM. So if this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction, we define the touching point of the extended, we define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right lower triangle OSN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this previous angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this previous angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that the upper right triangle PQO is similar to the lower right triangle, triangle OSN, this triangle. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the figures of this right upper triangle PQO are correspondingly equal to all the figures of this right lower triangle, triangle OSN. And therefore those two right triangles are similar to each other according to angle similar to. And again, if you found out that the upper right triangle PQO is similar, this is the sum of similar to the right lower triangle OSN according to angle similar to. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle OSN or side PQ of the upper right triangle PQO is equals to side OS of the right lower triangle OSN over side PO of the upper right triangle PQO. And again, we will derive that SN over PQ equals to OS over PO. SN is the missing side, so we know it is PQ is the right segment that we are looking for. In this question, it is equals to x. We have to find out the value of x. So PQ equals to x, SO equals to 2, according to what is given in the question. And PO is the radius of the circle, that is 3. So in total, we found out that SN over x equals to 2/3. Here we multiply this equation by x, and finally found out that the missing side SN equals to 2/3 x. Again, the missing side SN equals to 2/3 x. This is the missing side SN. This equals to 2/3 x, 2/3 times x units, and it's done. In the next step, we defined this angle as beta, and we focus on the green right triangle SNM. The green right triangle SNM, this angle equals to beta, this angle equals to 90 degrees, and therefore this reference angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the upper right triangle PTM, this angle equals to beta, and therefore angle beta is a common angle that belongs to both triangles. It belongs to the great triangle and belongs to the big right triangle PTM. So in the big right triangle PTM, this angle equals to beta, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus beta, according to the symbol that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this green small triangle SN according to angle similarity rule. So why those two right triangles are similar to each other? First of all, this is angle beta, that is a common angle that belongs to both triangles. So we can find out that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So I should prove that all the figures of this big right triangle PTM are correspondingly equal to all the figures of this right small great triangle NSM. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green right triangle SNM over side PT of the big right triangle PTM is equal to side SM of the green right triangle NSM over side PM of the big right triangle PTM. Because again, we derive that SN over PT equals to SM over PM. SN equals to 2/3 x over PT. PT equals to A according to our definition. And it is equals to SM. SM is the missing side, so we leave it as it is, over PM. PM is the diameter of the circle, the radius is 3, therefore the diameter is 6. So PM equals to 6. So in total, if you found out that 2/3 x over A equals to SM over 6. Here, because multiply this equation, if I found out that according to equation 1, 2/3 x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this equation 1, we have 4x, so 4x equals to ASM. So again, according to equation 1, we have to find out that 4x equals to ASM. In the next step, I presented to you Rule 15 and implemented Rule 15 in our drawing. According to Rule 15, if chord AB intersects with chord CD at point O, then the following equation is true that AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. According to this Rule 15, the following equation is true in this drawing. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement Rule 15 in our drawing. In our drawing, we have chord TM intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of Rule 15 are satisfied, and therefore we can implement Rule 15. And again, in our original drawing, chord TM intersects with chord AB at point S. So according to Rule 15, the following equation is true. That TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. And again, according to Rule 15, the following equation is true. That TS times SM equals to AS times SB. TS is A times SM. SM is the missing sign, so it is. So in total, in this version 2, we have A times SM equals to AS. AS in total equals to AO, that is the radius of the circle, that is 3, plus OS, that is 2. So in total, AS equals to 3 plus 2, that is 5, times SB is 1. And again, AS is 5 and SB is 1. So in total, we found out that according to equation 2, A times SM equals to 5 times 1. 5 times 1 is 5. So in total, according to equation 2, we found out that A times SM equals to 5. This is according to equation 2, while according to equation 1, we have only found out that ASM equals to 4x. We have two different equations for the expression ASM. Therefore, we can do the equation 3 that states that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times SM according to equation 1 is 4x, and it must be equal to A times SM according to equation 2. A times SM according to equation 2 equals to 5. So in total, according to equation 3, we actually found out that 4x equals to 5. Here we divided this equation 3 by 4, and we found out that x equals to 5 quarters units. 5 quarters is 1.25. So if you found out that the length of this line segment PQ that is equals to x is equal to either 5 quarters units in its length, or in terms of numbers, the length of this line segment PQ that is equals to x is equal to 1.25 units in its length. Okay, thank you very much.